is an organic chemistry question. It says, by using a base-catalyzed mechanistic equation, show that propanone and prop-2-enol are keto-enol tautomers. Tautomers are just isomers with the same molecular formula, but the only difference is the position of proton in the molecule. Let's represent this as CH3CO CH3. This is just skeletal formula, and this is the structural formula. And this CH3 here, COH, double bond, CH2. The molecular formula is 3 carbon atoms, 6 hydrogen atoms, and 1 oxygen. Here the same. 3 carbon atoms, 1, 2, 3, 4, 5, 6 hydrogen atoms, and 1 oxygen atom. But the only difference is that there are 3 hydrogen atoms here at the end, but here there are 2 of them. 1 attached itself to oxygen here. That is why 2 of them are tautomers. Remember that this is ketone and this is enol. The functional group CO makes it a ketone, while the functional group OH makes it ol, and the functional group double bond makes it in. That is why this is enol and this is ketone. Now let us write the mechanistic equation to show that these two compounds are tautomers. So I'm going to start from this ketone. You know, a base catalyst releases hydroxide ion. This is that hydroxide ion with a negative charge on oxygen. What now happens is this. This oxygen is highly electronegative. So it is going to abstract electron from this double bond, making this carbon-I-carbon partly positive. The 3 protons here, remember there are 3 hydrogen atoms here. There are 3 of them here. One of these protons will be sacrificed for the positive charge on the carbon atom. Therefore, this proton will break its bond here into this place to establish a double bond here. And this will result in partial positive charge on this proton. First of all, the oxygen, being electronegative, abstracts electron from this double bond, breaking this double bond and making this carbon have 3 bonds instead of 4. Because of that, carbon will have a positive charge. One of the hydrogens here will sacrifice for this positive charge on carbon. How? This hydrogen will forfeit the bond pair, the bonded electron here, and transfer it to this bond, making it a double bond. And the positive charge will be transferred on this hydrogen. Once we have H+, there is a negative charge. It will be transferred to this proton. At the end of the day, we are going to have an intermediate known as enolate ion. This double bond becomes single bond here, and the oxygen here will acquire a negative charge. Right? Now, there is an establishment of double bond here because bonded electron moved into that place. This is enolate ion, intermediate. Now, enolate ion is formed because a proton was transferred to hydroxide ion to form water. Look at that water. Now what happens is that the oxygen in water will collect the bonded pair, and this hydrogen becomes positive, and therefore the negatively charged oxygen will donate excess electron to this, and we are going to have this OH double bond. This is our enol, and we now have our regenerated hydroxide ion, which is OH with negative charge. This proves that this OH is actually a catalyst. This is where it has been regenerated, showing that these two compounds are ketone and enol. This is this, and this is this. This mechanism shows that these two compounds are keto-enol tautomers. If you found this video useful, comment, like, and share it as wide as possible. Click on follow or subscription button